All right. So this is the 12th lecture. I'm actually blanking right now. There are 4 conditions of extra stuff that we're assuming for the canonical linear programming problem. We were assuming A is m by n with m less than n. I know B was not fewer than m rows. B was greater than or equal to 0. Was it the rank of A was m? I think that was the last one. Right? I think that was the 4th condition. The rank of A is m. So that we don't have 2 rows that were linearly dependent. Because if we did, it would either be inconsistent or it would be redundant. So in either case, we could remove and have a simpler case. All right, so what did we do last time? So last time we proved how we can use phase 2 to solve phase 1. We showed that given a basic feasible solution to a related problem, we could get a basic feasible solution to the original problem or show that no such solution exists. So what we can now do is, whenever we're given a canonical linear programming problem, we can now assume that there is a basic feasible solution or that the problem has no basic feasible solutions. There will be situations where there will be no basic feasible solutions. If I give you a diet where you have to have a certain number of nutrients, but you also have a cap on how much you can have of things, that could prevent a feasible solution from existing. Okay, now that we know a basic feasible solution exists or doesn't, we now want to find a basic optimal solution. Okay? Is there any loss in going for basic optimal versus optimal? If we have an optimal solution, do we always have a basic optimal? Yeah, we proved that result, and we actually have a nice way that allows us to go from one to the other. So if we have a basic, so if we have an optimal, it's really easy to pass to a basic optimal. So for the rest of the day, let's assume that there's a basic feasible solution and try to find either a basic optimal or prove that none exist. Why? Well, if there's no basic feasible solution, there's really no point in trying to find a basic optimal solution. So without loss of generality, assume there exists a basic feasible. And now we want to do phase 2. Find a basic optimal or prove none exist by a sequence with costs going to negative infinity. So what's nice is if there's not a basic optimal, not only do we not have a basic optimal, but we have a sequence of solutions where the cost is getting more and more negative all the way down to negative infinity. We don't have to worry about maybe the costs are getting closer and closer and closer to 15, falling down from above. Okay? This is one of the nice things. We are looking at a compact space. The other thing to look at, or at least we can quickly restrict ourselves to a compact space. How many basic feasible solutions are there? So how many basic feasible solutions are there? What word would you use to describe it? Or phrase? You look like you're mumbling some. How many basic feasible solutions are there? Are there an infinite number of? A large finite. Which is it? Infinite or large finite? Large finite. This was the whole point about passing to basic feasible. For basic feasible, the corresponding columns of the matrix are linearly independent. There's only finitely many ways to choose columns, to choose a finite set of columns. And each one of those will generate at most one basic feasible solution. So there are only finitely many basic feasible. So what we could do is we could just list all of those. And so as long as we stay within basic feasible solutions, there's only finitely many, and we won't have something like this. Now, we could have a situation where the cost goes all the way down to minus infinity. That's possible. But it won't be going through basic feasible solutions. Okay? Any thoughts on what we might use to try to figure out when we have an optimal solution? What result from early in the semester might help us figure out that we have an optimal solution? I'm sorry? The objective function. What in particular? I'm sorry? Well, but how do we know when we've minimized it? How do we know that there's not a better choice? What did we prove that allowed us to tell, we've hit the minimum? We had a result that allows us to do that. I'm sorry? Gradient implies differentiability. We don't necessarily, things are linear, but we proved a result about a related problem. This is where we had the dual problem. And we showed if y was feasible for the dual, and y transpose b equaled c transpose x, and x is feasible, then not only is it feasible, it's optimal. So this became a condition to tell when we hit optimal. Okay? So now we're finally going to get dividends for that result from a while ago. It's going to be a way to tell, have we hit the smallest possible? And so if we can find a feasible solution for the dual problem, and there's a gap, that doesn't necessarily prove that x is not feasible. That doesn't necessarily prove, that x is not optimal. It just might be we took a really bad feasible solution for the dual problem. Right? It's not saying that every feasible solution for the dual problem will have its cost the same as the cost for the original problem. It's just saying if we happen to find one feasible solution for the dual problem where its cost equals the cost of the original problem, then we know the feasible solution to the original problem is actually optimal. Okay? So we've got to be very careful about which directions we prove things. All right, so the first, I'm trying to decide exactly how much of the algebra to do today, is we have a dinky lemma. So lemma. If x is a basic feasible, then x has exactly m non-zero entries. Okay, so this is the first result we need. Why would something like this be true? So I'm saying that if we have a basic feasible solution, then it has exactly m non-zero entries. It's on the board. Yes?
We need B to be a linear.
Yeah, we need B to be a linear combination of exactly m rows. Oh, I'm sorry, exactly m columns. We're not choosing a degenerate B. We're not choosing a B lying in one of these lower dimensional hyperplanes. We're saying we can't get B unless we use m columns of A. And so, by our additional assumptions, this follows. So proof by assumption on P. So what this is going to help us do is in the analysis is we can always assume when we have a basic feasible solution that there are exactly m non-zero entries. Otherwise, we would have to break up into many different cases. And it would depend on, well, what do the columns look like? And so this greatly simplifies things. It does make the method a little bit more specific. It's not going to hold for every problem. But the probability that B lies in a m-1 dimensional subspace is negligible. And you can always tweak things a little bit, and for the most part, it's not going to really matter. Think of it as you are doing a problem for the oil industry. You're shipping oil between various refineries and cities. And you tweak how much oil New York City needs by 1/4 of a gallon. Right? That's not going to really affect how much oil you're sending to the different places. It does, however, make you worry about the stability and maybe the runtime. Is that maybe if B is very close to being a linear combination of m-1 columns, maybe the runtime will be longer. Or maybe I'll have some stability issues. This is definitely something you have to worry about if you are trying to find eigenvalues of matrices by using the determinant formula. How stable is your algorithm? Nobody who does this professionally uses the determinant of A minus lambda I to find eigenvalues of large matrices. You do not want to be writing down a characteristic polynomial of a 10,000 by 10,000 matrix and trying to solve a polynomial equation. So you really want to have some sense of how you should be doing this. All right, so now we have this lemma. So the first thing we're going to do is, without loss of generality, let x1, x, m be the non-zero entries. I don't really need to do this, but this is just going to make it a little bit easier for me when I'm writing things. And we're going to let A sub B be the trimmed matrix corresponding to these entries, or these columns. Because when I'm trying to solve AX equals B, if all the other entries of X are 0, those columns don't come into play. So we're really studying, say, AB XB equals B. And the letter B here is for basis. These are like the basis columns. These are the columns that are coming into play right now. The other ones don't really matter. Okay? Any questions so far? Do you think we should be able to solve this? So do you think this equation is solvable? What have I assumed about X? Yes.
Just to clarify.
Yep.
So this is a m by m matrix.
This is an m by m matrix.
Cross with an m by 1 vector equals an m by 1 vector. Right?
Oh, so wait. Do I want to trim B? Good question. No, I think.
Yeah, it's fine. This is like.
Yes.
Correct, right?
Yes.
This isn't like to throw you off.
No. Okay. Yeah. Yes. Because B is going to have m components. Yes. Now, for a second I said, oh no, did I drop something? Is it B sub B? But it's just B, not B sub B. Right? It's to B or not to. Yes.
So we know that the A is, all the columns in A are linearly independent.
Mm-hmm.
And so it should be invertible.
So A is definitely invertible, but we need the entries of X to be greater than or equal to 0. So will this be solvable? It's solvable for a trivial reason that I'm assuming we start off with a basic feasible solution, and that's X. So this will be solvable. We do have an invertible matrix, so we can put that over there. Okay? So from this point onward, all it is just doing a bunch of linear algebra. So we can consider YB, oh no, sorry, just Y, sorry, Y transpose AB, and here I do want to trim the vector, equals C transpose. And now, because we are assuming that this matrix is invertible, we get Y transpose equals CB transpose AB inverse. And as soon as you see Y, what problem should you be thinking about? The dual problem. Now what's nice about the dual problem is we don't have to assume that the entries are greater than or equal to 0. We just are assuming that the entries are real. So if we have a solution, if it satisfies the constraints, we're fine. And so this is going to be a nice solution. The problem is it's only looking at a subset of the entries of C. We're not looking at all the entries of C. And so in order to be a feasible solution, we need this inequality or these inequalities to hold for every entry. This only holds for some. So we need to make sure that this holds for every component and not just the components we care about. Over here, okay. So this is a solution to this equation, but this may not be feasible to the dual. So we have two cases. Case 1, Y is feasible for the dual. And now what we're going to do is we're going to calculate an inner product two different ways. I'm going to write it, I think, slightly different order than the book. I'm going to start off in the middle with Y transpose AB XB. So I'm going to start off like this. If I'm writing it like this, I can look at it with these two together first or these two together first. If I look at these two together, y transpose AB, that's our vector CB transpose. So we get CB transpose XB. And if we look at it the other way, if we're assuming it's feasible, then this over here, this is just B because X is feasible to the original, and we get Y transpose B. And now we have our condition, this implies optimal. Okay? It's not bad to just go through the algebra slowly, but this is the same thing we've done time and time again. We start off with an expression and we group things differently. One way is we group these two, the other way is we group these two. How many of you have proven properties of eigenvalues of matrices in your linear algebra class? Do you ever do these grouping things here? When you're trying to find, is the eigenvalue real? Is it absolute value 1? One of the ways you prove stuff like this is by grouping things and looking at ways you do things. So maybe if this time at the end of class today, I'll talk a little bit about how you do that because it's a really nice idea. Okay? So in the case when y is feasible to the dual problem, we immediately get a solution. So case 2, y is not feasible. All right, so what does it mean if y is not feasible? Then it means there's got to be some component where y transpose AS is greater than CS for some column. It's the index. So I don't know if it's the first, the second, third, yes. It's for column S.
Is it still CS transpose?
Over here? No, because now I'm looking at a specific entry. So if it's not feasible for the whole thing, there's got to be some column for some S. And in fact, we know that S cannot be in what set of indices? We know S can't be in a certain set of indices. Which set of indices must S avoid? What are the ones from X? 1 through n. Right. So we're using B to represent the basis. Here it's 1 through m. Because for those ones, we've got over here that y transpose is CB transpose AB. That in those components, everything is working out fine. So now the question is, what happens here? We've got some component where this is positive. Okay? The rest of it is just straightforward linear algebra. It's time-consuming, but what we're going to do is the same trick we've done before. We want to switch this column with one of the columns in B. So what this is saying is the cost coming from this is too high. If we make a column switch, we can lower the cost. And the cost will be strictly smaller. So this should remind you of the method of descent. In the method of descent, what we did is we started with a solution, and we found that there was a new solution with a smaller value. When we were looking at the square root of b as a over b, we said, given a solution with a and b integers, we can find a new solution with the denominator smaller. Lather, rinse, repeat. Do it again, 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 again. There is such a thing as the smallest positive integer. Right? We can't do this infinitely many times. If every time you do this, the cost strictly goes down, and there's only finitely many possible basic feasible solutions, that means there's only finitely many possible basic optimal solutions. At some point, we would hit the minimum. So what's really going on is when we do phase 2, we have two different cases. We have case 1, where the corresponding y is feasible for the dual, or case 2, it's not feasible, at which point there's got to be some column where the cost is worse. And what we'll do is we'll switch out one of our columns for that new one. We've got linear independence among the columns, so we can write AS in terms of these other columns. And we'll replace it, and we'll get a new basic feasible solution with a lower cost. We then run phase 2 again, and we're either in case 1 or case 2. If we're in case 1, we're done. If we're in case 2, we run it again. The only way we lose is if we always end up in case 1. I'm sorry, case 2. Can we always end up in case 2? No. Okay. So eventually this should stop. If there's an optimal solution. If there's not an optimal solution, what would happen? We might be able to get a new solution here where we can just drive the cost all the way down to negative infinity. So when we're over here, we lowered the cost. Maybe we can really lower the cost. So when we were doing things before, when we were proving you're given a feasible, there was a basic feasible, we looked at a whole family of feasible solutions. We introduced a parameter t. Right? And we said, if this is a solution, then for every value of t, this is a solution as well. And then we chose a critical value of t to make something vanish. And then we got one fewer non-zero component. We're going to play the same game over here. What we want to do is we want to replace one of the columns with this new column AS and lower the cost. And that's where things get a little tricky. When we do this, we're going to get a parameter. And the question is, will there be some critical threshold where one of the components becomes 0? And if so, if we then continued, one of the components would then become negative, and we would have a contradiction. So can we keep doing it only to a certain point? And if we can only do it to a certain point, then something vanishes, and we now have a new solution with exactly m non-zero components. Or can we just let our parameter go off to infinity? And if that happens, then we'll have a sequence of feasible solutions with the cost going to negative infinity. So really, case 2 is a little bit more complicated. Case 2 has 2 subcases. So there'll be 2 subcases. So there'll be subcase 1, parameter can go to infinity, cost goes to minus infinity, and then there'll be subcase 2, parameter is bounded. Finite lower cost. Okay. This is where it's really important to have done the reading before class so that this is not the first time you're seeing all these arguments. All right, so to get a sense of have you read enough before class, this should be vaguely familiar. The details of the algebra maybe not, but this rough idea that we're going to have these 2 subcases and that the argument's going to be proceeding like this, that's how much you should have been reading beforehand. If this is seeming new, this means you're not preparing enough for class. Okay, so now let's really step back and see what goes on. All right, we start off, we do phase 2, we input a basic feasible solution. Yes? No, remember when we had the parameter t when we were going from feasible to basic feasible? We're going to be having something like that as well. I think they call it lambda in this case, so it looks different. So we're going to have some parameter, we get a family of solutions. And so when we run things, what's going to happen is if we ever end up in case 1, we're done, and we found an optimal solution. So if we don't end up in case 1, we end up in case 2. And when we're in case 2 has 2 subcases. In one subcase, we have, when we look at our family of solutions, we have the ability to go all the way to minus infinity for cost. We can do that because we're never sending a coordinate to a negative number. So they always stay feasible, and the cost just keeps getting smaller and smaller and smaller, all the way down to negative infinity. And if this is the case, then there's no optimal solution. Okay? If we are in subcase 2, then that means that the parameter is bounded. We can only send it to a certain point before one of the coordinates becomes 0. And at this point, we have m plus 1 coordinates. When it becomes 0, now we go down to exactly m. We don't have to worry about going down to m minus 1, because then that would violate b being a combination of fewer than m columns. And so if we're in subcase 2, we get a new basic feasible solution with strictly lower cost. And then we run it again. So the only danger is not hitting case 2 infinitely many times. It's hitting subcase 2 of case 2 infinitely many times. But we can't hit subcase 2 of case 2 infinitely many times because there's only finitely many basic feasible solutions. So the number of times we can be in this case is bounded by the number of basic feasible solutions. And that's going to finish the proof. Okay? So we're going to use all the different stuff we've been looking at. As a quick aside, just to get some sense that things like this could happen, let's consider, how do I want to do this? X plus y do this. No, I'll hold off on doing that now. I want to make sure I can get through this whole argument first. All right. So we don't need this anymore. Is everybody comfortable with all the different things we're assuming for our canonical linear programming problem? The real big one is that B is not a linear combination of fewer than m columns. Okay. So now let's do analysis of case 2. So I claim AS, I want to use the same notation as the book. I claim I can write it as the sum of, I think we're doing TJ, AJ, J is in B. This is because the columns of A corresponding to my basic feasible solution are linearly independent. This is from linear independence of the columns in AB. So in particular, AS minus the sum J in B of TJ, AJ, what does this equal? The 0 vector. What if I multiply this by lambda? Still equal to the 0 vector. Right? This is the nice thing about having a combination like this. So now what I'm going to do is let's look at, we know AB XB equals B, or AX equals B. And the entries of X are greater than or equal to 0. We want to get a whole family of solutions. If you look at this, this is telling us how we can change the entries of X. If we take this combination of the columns, it's not going to affect whether or not AX equals B. So we can look at a new vector X. And so we're going to look at, I want to use the same notation, X prime is going to be defined by the following. Xj prime will equal lambda if j equals s, xj minus lambda tj if j is in B, and 0 otherwise. So what we're doing is we're taking a vector x and we're tweaking the coordinates. In the s column, we're putting in lambda. What was the element in the s column before? What was the element in the s column of x? Your x was our basic feasible solution. What was the initial entry of x in that column? 0, right? X was a basic feasible solution. We were assuming that it was the entries 1 through n that formed our basis of columns, what we were calling B. And we are assuming that y is not feasible for the dual, so there's some column that's not in our list. Because over here, we know that everything was working in through here. We had equality, so if we have an inequality, it can't be from one of those first m entries. So we know initially, just to have some kind of similarity, xj was 0 if j equals s. It was xj if j is in B, and 0 otherwise. So we're seeing how we're changing our vector. In the components corresponding to the basis, we're now decreasing them by a little bit, or increasing depending on whether or not lambda tj is positive or negative. And then in everything else, we're keeping it unchanged. So we're only changing m+1 entries of our vector. One of them is being told from us which one we should do. Now, which one would you choose? We have to choose something where, y transpose AS is greater than CS. Maybe you choose the one where that is the largest greater than of all of them. You're very similar to look at the gradient and move in the direction of maximum change. Look at the one where we are missing by the most, where we are furthest away from equality, and try that one. Doesn't really matter. That would be to make the algorithm run faster. Right now, all we need as theoreticians is that there is some choice to make. Then when we want to implement it, we would want to try to make the best choice. And the hope is maybe it's somewhat simple. At each moment, do what is best locally, and that will lead to what is best globally. Okay, so now we have these new vectors, this new vector over here, and this is a whole family of them. So I could actually put a lambda over here to emphasize the fact that this is a family of solutions. So I don't think I've done this in the book. I think I like the lambda. Well, do people care? Do people want the lambda? Do people want the primes? All right. No one has any preference. I'll keep it as the primes, but we'll be aware that for every choice of lambda, we get a different solution. Can someone give me one value of lambda where this will still be feasible for the original problem? Some value of lambda where it's still feasible. Yes?
The min lambda.
I'm sorry?
The minimum lambda.
That's too much work. 0. Right. Always, always, always go for the smartass answer first. Then be clever and try to get the best lambda you can do. The simplest one is still feasible if lambda equals 0. Okay. Now what we know is since it's feasible if lambda equals 0, we should be able to increase lambda and have it stay a solution for a while. So the difficulty is if something becomes negative. So when we're looking at what's going on here, as lambda gets larger, this stays positive, or becomes positive. That's great. The only danger is if one of these becomes negative. Well, if one of these becomes negative, it has to first hit 0. So what we do is we keep increasing lambda, and we see, can we increase lambda to infinity? So for instance, if all the tj's are negative, then we could send lambda to infinity. So if all tj are less than 0, or I guess less than equal to 0, well, we wouldn't have a tj, yeah, I guess less than equal to 0, can send lambda to infinity, algebra shows cost goes to negative infinity. So I'm not going to go through and do the calculation of what the new cost is. I'll just say what the answer is. New cost minus old cost is equal to lambda CS minus the sum J in B of Tj Cj. And so with a little bit of work, you can show that the cost is going to be decreasing. What if one of the tj's is not negative or not 0? What if a tj is positive? If a tj is positive, cannot send lambda to infinity. Right? So if one of the tj's is positive, then eventually there'll be a critical value of lambda, xj divided by tj, where we'll stop. So can go to the minimum over all j such that tj is less than 0 of something like xj over tj, something like that. We know xj is positive. Okay, so sorry, we want tj greater than 0, sorry. Right, and I don't even need the absolute value signs now. So if there is some tj which is positive, say tj is 5, then I can go all the way up to xj over 5. And then I look and see which is the minimum of all these numbers. And that will give me a critical value. And I go all the way up to that, and when I hit that critical value, a new component becomes 0. So when you look at this, before we had, for positive values of lambda, we had m plus 1 entries that were not 0. As we now increase lambda up to this critical threshold, at least one component here becomes 0. This is non-zero. Is it possible that two of these things could become 0 at the same moment? It's unlikely, but is it possible? It is. But if that happened, then B would be a combination of fewer than m columns, and that's a contradiction. So because B is not a linear combination of less than m columns, new feasible solution is basic with m non-zero entries. Okay. And this essentially finishes the proof. So again, I'm not going to do the algebra of looking at the cost. It's just going through and collecting all of the linear algebra and all the inequalities. The idea is the same as before. We keep coming up with these families of solutions, and we keep having some kind of minimality property. Here, the minimality property is not going to be the number of non-zero entries. We're always going to have exactly m non-zero entries in our stuff here. But what we will have will be the cost. If we ever get into a case where we have a feasible solution to the dual, we're done. If not, then we have to have this new family. And so the only question is, think of lambda as a dial that you can turn. Can you turn lambda all the way to infinity? If so, you can then send the cost all the way to negative infinity. And there will be no optimal solution. Okay? If not, if there's some finite value of lambda where once you hit that a component becomes 0, then you get a new basic feasible solution with strictly lower cost. And so lather, rinse, repeat, you can't do this infinitely often, and thus eventually you will either have a chain going to minus infinity, or you will have an optimal solution to the original problem. All right, so this finishes the analysis of phase 2. What's wonderful about this is extremely constructive. It tells you exactly what to do at every moment, and not only does it tell you what to do, but if you don't have an optimal solution, how do you know you don't have an optimal solution? You don't have an optimal solution because you see the cost going to minus infinity. That's absolutely wonderful. Okay? All right. So what I'm not going to do is I'm not going to go through an analysis of the runtime. If somebody wants to, as a really good exercise for, for extra credit or for a project for this class, really good theoretical stuff, is talk to me about how you would determine how quickly this algorithm works. This is why I've done things like the Euclidean algorithm, to show you that things that seem initially are going to take a long time to run could actually run very fast. So in practice, the simplex method runs very quickly. We will get very soon to integer programming, which I think is a lot more fun. So in integer programming, things are either on or off. You're doing it or you're not doing it. American Airlines, allegedly, it's supposed to be 0-1. You could technically be flying some flights on American Airlines. And you're trying to decide, I have some constraints. What is the optimal schedule? This is an extremely important area. And for my computer scientist students, what do we know about binary integer programming? It's NP complete, unfortunately. So these are very difficult problems to look at. If we could solve these, we could do an enormous number of things in computer science. We do not know fast ways to do binary integer programming. Fortunately, we do know fast ways to get close to the optimal solution. If you are trying to minimize, one of the big problems is the traveling salesman problem. You want to hit a bunch of cities, you want to hit each city once and only once, and you want to minimize your total travel time. If your total distance is on the order of 4,000 miles, and you have a schedule that is within 600 feet of optimal, you don't really care that much about the final 600 feet. It's so much lower order that it doesn't really matter. And so for a lot of problems that we can't solve, we can at least get close enough in a reasonable amount of time that it's good enough. And this becomes a nice way to segue back into the chess problem. The chess problem was a lot harder than I initially thought it was going to be, but it's very interesting, and the analysis of it leads to the opportunity to talk about a really good method, is how do you get a ballpark feel for the solution. So this is building on what we did here. What we did here is we used the dual problem to get a sense of, how close are we to the optimal solution. Any feasible solution to the dual problem gives us a lower bound for the cost that we're trying to minimize. And so if we have a lower bound for the cost and we compute our cost over here, we don't know exactly where the optimal cost is, but we know we're off by at most this much. And if they're extremely close, then we know, okay, even if we're not at optimal, we're so close to optimal we don't care. So one of the things I want to do for something like the chess problem is I want to get a sense of what is the true answer. So I know some of you were looking at the chess problem and someone got up to 11. Has anybody beaten an 11 by 11 board? All right, so if you got up to 11 by 11, email me for extra credit. You've won. All right. I'd love to know what the answer is for a 20 by 20 board or a 30 by 30 board. That's beyond our computational power. But here's something that may not be beyond our computational power. Do we have an idea of what the answer looks like? So for the chess problem, it was 0, 0, 0, 1, 3, 5, 7. What was after 7? Was it 11?
Yeah.
22? 18, then 22? And so we want to know what are the terms in the sequence. So if we let Pn be the number of queens, what I'm going to do is I'm going to prove some constant C1 n to the 3/2 and n squared minus some constant n to the 3/2. And this is, I think, around 4, and I think this was around 1. We'll see in a moment. The lower bound is much easier to get than the upper bound. And the reason is for the lower bound, all we have to do is find one good configuration to analyze. And if we analyze that, and we know how many pawns we can safely put down, then that's a lower bound for the optimal. And so what we saw is, if we have an n by n board, what we could do is we could take a square root of n by square root of n subboard. I really am not going to play games with the floor function and whatnot right now. These kill everything in that column, these kill everything in this row, and then we have all these different diagonals. And so what's killed, it's going to be less than equal to n times square root of n for these columns, n square root of n for these rows, and then the number of diagonals I have is going to be 2 root n minus 1 times n. And again, not all the diagonals will have n. I'm going to be double counting some of this stuff, but the double counting is going to be lower order. So when the dust settles, what you get is killed is equal to 4 n to the 3/2 plus an error of lower order. You can do a better job and analyze this. I think it's going to be an order n error when you figure out exactly what you're double counting. I don't really care. The main term is going to be of size n to the 3/2. Question?
Yeah, I was saying the way we did it was we calculated the triangles, and it was way easier.
Oh, okay. What did you do?
You just calculated the triangles right there, like the blank spaces.
Oh, over here?
No.
Oh, right here. Oh, I see. You did, yes. And that will give you an exact answer. Yes. Just double it, not square. Oh, by square it, you mean convert it to a square by putting the two together, as opposed to squaring the number of entries. Yes. Right. So good. So yes. So that's even better. So if you use triangles, you can get exact very easily. And do you get 4 n to the 3/2 as the main term? Yeah. That should be the n to the 3/2 term. Okay. So this gives us the lower bound. Now we want to get the upper bound. What makes the upper bound hard is it has to work for every configuration. The lower bound we only have to have work for one configuration. So how do we get the upper? So consider any configuration. Assume we have f of n rows with queens. This kills at least n f of n squares. Because each row with a queen, all n squares in that row are inaccessible. It kills more than this because it's going to kill some things in columns, but maybe I have queens on top of each other. I know I have to kill at least n f of n squares. So we agree on that. Now let's consider the columns. So the more columns with queens, the more squares are killed. The worst case for us is, what is the fewest number of columns with queens? What is fewest number of queened, I think that's a word, columns? If anybody plays Scrabble and successfully uses queened, I will give you extra credit. Okay? How many columns could there be with queens? What's the minimum number? Well, we know there's at most, we know there's exactly f of n rows with queens. So the most queens we can have in a column is f of n. Cannot have more than f of n queens in a column. If we did, we would have more than f of n rows with queens. We have exactly f of n rows with queens. Therefore, at least n over f of n, I think I'm going from lowercase to uppercase. N equals n. So we have at least n over f of n columns with queens. And this kills n squared over f of n squares. Okay? So we're almost done. We have two different bounds on the number of squares that are killed. One is coming from looking at how many rows. One is coming from looking at how many columns. Okay? So the number of killed squares is greater than or equal to the maximum of f of n times n and n squared over f of n. So we want to make this as small as possible. I claim we want f of n to equal n squared over f of n. Imagine this term was larger than this term. Then we would decrease f of n, and that would lower the maximum because this would then go up. If this term were larger, we would increase f of n, and this term would go down, and then this term would go up. So the optimal choice of f of n is when these two things are balanced. This is an extremely common technique in mathematics, is we have two competing influences. What should we do? We make them equal. If they weren't equal, we could improve things. Either have f of n go up or have f of n go down. So where are they equal? Well, I can kill one of the n's and I get f of n squared equals n. So we get f of n equals square root of n. Therefore, we kill at least n to the 3/2, as claimed. So what I love about this is we have the correct order of magnitude for what the answer is. It's on the order of n to the 3/2. So we have a constant of 1 here, we have a constant of 4 here. What the actual value is, what lower order terms are, I don't know. But I know that the number of squares that are killed in the optimal configuration is on the order of n to the 3/2. And it's really nice to be able to get an answer like that without too much work. All right, I'm going to assign an extra problem related to this because this is so important. You are not allowed to use homework exemptions on this problem. Okay. All right, have a good day.